Hey guys, it's Sam Gralla here, bringing you a video about the divergence of a vector field. Now there's lots of videos on this topic, but one thing I haven't seen addressed properly is the real meaning of the divergence with an honest formula. And this is kind of a pet peeve of mine dating back to when I first learned the divergence 20 years ago, that there were a lot of words bandied about and pictures involving spreading out and etc., but there was never sort of a formula given to you backing up those words. And so I thought I'd derive that formula for you today. We're going to call the vector field W, and I'm not going to call it V because we're going to use V for the volume. So the volume of a region, V, changes with time according to dV dt equals the integral over that region, which I'm going to call d, of the divergence of that vector field. Now I'm writing little arrows, and I'm thinking about 3 dimensions, but actually this holds in any number of dimensions. Now to explain what everything means in this picture, let's make a vector field. So let's draw some vectors. It doesn't really matter so much what the vector field is, as long as it has some divergence. So we'll sort of draw something that looks like it's diverging. And let's consider a region of this vector field. So here it is. I'll just draw it in blue. Doesn't matter so much what it is. Let's shade it in yellow. And let's imagine flowing along this vector field, this region. Now, I'll make this mathematically precise, but for now, let's just sort of imagine drawing some curves that are everywhere tangent to these arrows. And that's what's meant by flowing along. Physically, if this were the velocity of a fluid, you could drop some petals in the water and watch them flow along. So we have this region, and we're going to follow it for some amount of time. And then we're going to have some other region, that is the new region, flowing along this vector field. And so if these regions are called D, so this one here will be D0 for the initial region, this one here will be D at time t, then the claim is the volume V of these regions obeys an equation. Its change in time has to do with the divergence of the vector field W integrated over that region. Okay, so that's the claim. That's the formula. And what I'm going to do now is derive you that formula step by step. And it involves some math that, if you're sort of very advanced in your studies, is natural to you. But if you're newer, you've learned it all, but you may not have put it all together. So I'm going to go nice and slow, step by step. Now, the first step is just to remind you what a curve is. Okay? So we're going to think of curves as parametrized curves. Okay? So what that means is there's some parameter t that we're going to call time, but it doesn't have to be. And we just give x, y, and z, which I call vector x, as a function of time. And that gives us a curve through space. Now, there's a concept of a tangent vector to a curve, like that. And what is the formula for the tangent vector to a curve? Well, it couldn't be simpler. It's just dx dt. Okay? And so that's the tangent vector. All right. And so that's all we're going to need for curves. So that was step 1. That wasn't so bad. Hopefully that was easy review for you. Okay? Curve x of t, tangent vector dx dt. Step 2. Now we need to talk about what's known as the integral curves of a vector field. So I'll just call it W. That's our vector field. Okay? So let's go ahead and do the integral curves of a vector field. So now let me draw a vector field again. Let's just get a smaller one here. What if we want to make this red line here? We want to make a mathematical formula for the idea that we draw this red line that is everywhere tangent to an arrow. Okay? Well, we just went over what the tangent vector is. It's dx dt, right? So the equation we want is that the tangent vector, dx dt, is just equal to the vector w. At whatever point x you're at, say this point here, you say, well, the tangent vector to my curve dx dt has to be exactly equal to w, and then you indeed get a curve that just sort of follows the arrows. Okay? So these curves are called the integral curves, and they're space-filling. You could start at any point, any of these red dots, pick any red dot, and just solve the equation, and you get the integral curves of the vector field. So that's the precise mathematical expression of the idea of flowing along a vector field. All right, first two steps are out of the way. We said what a curve is, we reminded you of the tangent, and we said if you set the tangent equal to the vector field at every point, then you get a family of curves called the integral curves of those vector field, which I've drawn in red. Okay, now step 3 is where it's going to get a little newer. The math is probably something you're familiar with if you've taken any multivariable calculus and vector calculus, but we're going to think about it in a kind of new way. Okay? So here's what we need to do. Step 3, we need to think about now the volume under the flow. So what's meant by this? Okay, so we're trying to talk about the volume of these regions, d0 and d of t. Now, what's the volume of a region? Well, it's just the integral d3x over the region, right? So let's write volume at time t is just the integral of d at time t d3x. All right, couldn't be simpler. But now what we're going to do is we're going to think about the volume as a function of time with reference to the original volume d0, which is going to help us get an equation for how it changes. So if we have a point here in the volume d of t we're interested in, and we call that point x1, we're going to imagine tracing back in time along x1's integral curve to wherever it started at the initial time t0. I'm going to call that y1. So these are both vectors since they're representing points in space. Okay, and we could take another point inside this volume, x2, trace it back, and I'm just going to call the original point y2. Okay, so now I have just a notation, but it helps me link the two regions. Okay, now here's the key idea. This defines a map. So we can think of this as a function x of y, right? Because you could start with any point y. We called them y1 and y2, but you could pick any one. You could flow along the red lines, the integral curves, for a time t, and you'd get to some point x. So we have a function. And this function changes coordinates for us. We can think of this as a change of coordinates relating x and y. That's the key idea of this whole thing. Because now, if you remember how integrals change under changes of coordinates, we need to put in here a factor of the Jacobian matrix, which I'm going to write as dx upper I, where I is 1, 2, 3, or if you're in d dimensions, 1 through d. dy lower j, where again, j runs 1, 2, 3, or 1 to d. The vertical bars mean the determinant, and now I have d3y, or ddy if you're in d dimensions. And what's the volume that we integrate, the region we integrate over? Well, it's not d of t now, it's d of 0, right? When we change coordinates to y, we integrate over the region spanned by y. Okay, so this box here is sort of the smallest of the steps, but this is probably the newest, all right? The idea is we write the volume at time t in terms of an integral over the coordinates y at time 0, and we have this Jacobian factor here that we need to calculate to make further progress using this function x of y defined by flowing along the integral curves. Okay, 3 steps done. So we've set everything up, and now we just need to calculate. So we're going to calculate this Jacobian determinant, and we're going to need a formula from linear algebra, which you can derive, but I'm just going to sort of put it up here. You may or may not have seen this one yet. It's very straightforward to derive. It says that the determinant of the identity matrix So this is, ones in the diagonal, identity, and zeros off the diagonal, plus some other matrix A is approximately equal to 1 plus the trace of A, and the approximation holds. I guess the easiest way to think about this is we can add higher order terms here. We can write plus order A squared. So neglecting terms of order A squared and higher, just keeping the linear order in A, we have this formula that relates the determinant of the identity plus A, which you think of as small, as 1 plus the trace of A. Okay, so that's a magic formula. I don't want to get too far afield deriving it, but we're going to need it for step 4, where we calculate. So we're going to calculate this Jacobian determinant, dx, dy, but we're going to do it for small t, because ultimately we want a derivative with respect to t, and by Taylor expansion, that's sort of the same thing as for small t. So that's what we have to do using this formula, and let's do it. Now remember the equation satisfied by x. The equation is over here, dx dt equals w. Solving that equation in general would be hard, but solving it for small t is easy. It's just the linear approximation from calculus. So we can just immediately write down the solution is x is approximately its initial value. If you don't flow very far at all, it's just its starting value, which we called y. And then the next approximation to the solution is, well, you just add w times t, and then there's higher order terms, order t squared. So that's the approximate solution for small t for the integral curves. All right, now we just take a derivative. We're trying to calculate dxi dyj. Well, the first term is just dyi dyj, and then the second term is dwi dyj. Let's make sure you can really see the differences between my i's and j's, times t plus order t squared. Okay, so that's our Jacobian matrix. Now we need the determinant of the Jacobian matrix. So let's do that. Determinant dxi dyj. Well, actually, first we should probably note that this first thing here, dyi dyj, well, if I equals j, that's just 1. And if I is not equal to j, we're taking the derivative of something with respect to something independent, and so it's 0. So this thing is actually the Kronecker delta, which is another way of writing the identity matrix. Identity matrix I. And then this one here, dwi dyj, we can't really do anything else with. Let's just write it again with clearer i's and j times t plus order t squared. And now we can do the Jacobian, dxi dyj, the Jacobian determinant, rather, that is the Jacobian. So we have the determinant of I plus something small. Well, that's our formula. Our formula said that the determinant of I plus something small is 1 plus the trace of the small thing. Okay? So we're going to use that down here. And it's going to become 1 plus the trace of what's the small thing? Well, the trace is this matrix dwi dyj times t plus order t squared. Okay, but now think, the trace of this matrix, right? Trace means sum the elements on the diagonal, which is the same as saying, well, diagonal elements are where I equals j. We sum the elements where I equals j. Well, all this is the trace, so we can pull the t out. So 1 plus t times the trace of this dwi dyj. Well, that's just dwi dyi summed over I plus order t squared. But what is this thing? w as a function of its coordinates yi. This is just the divergence. This is where the divergence comes in. 1 plus t divergence of w plus order t squared. And that's the formula we're going to need. So let's go ahead and highlight that so we have it for later. But that was the result of our much longer step 4, where our goal was to calculate this thing for small t. All right, we are almost there. If you stayed with me, congratulations. This is not easy stuff, but you're almost to the derivation of the key formula. And that's going to be step 5, put everything together. And let's do that. We have this formula here, which tells us that we're supposed to get that the volume at time t is this Jacobian determinant integrated. And we have the other highlighted formula down here, which tells us what that determinant is. And so we put them together and we find that for small t, v of t is equal to integral of d0, plugging in the Jacobian, 1 plus t divergence of w plus order t squared d3y. So all I've done is combine the two formulas. Now let's use the linearity of the integral. So the first term is integral d0 d3y. And then the next term is, well, we'll pull out t, integral of divergence of w d3y, and then order t squared. And we're basically done. Because this, if you think about the Taylor expansion of a function, the first thing in the function is the value at t equals 0. And indeed, we see that the volume at t equals 0 is the integral at t equals 0. So this is indeed just v0, the initial volume. And then what's the first term? Well, the first term in a Taylor expansion is always the derivative of the function. And so this thing here must be equal to the derivative of the function v dt, dv dt. You can think of this as a Taylor expansion, or if you're more of a mathematician, you'll probably just want to go back to the definition of the derivative and plug this formula in, and you'll find that indeed this integral is the derivative. And so actually, we're done. This equality, dv dt equals integral of divergence of w d3y, is actually what we wanted to describe from the very beginning. We called it x there, but it doesn't matter. Y is just another label. And so this is the formula. So if you made it through to the end, congratulations. And now, hopefully, you'll remember not only the honest formula that tells you what the divergence means, but also how to derive it. And what does it mean? Well, this is the precise definition. You have a vector field. You flow along the vector field in the sense of the integral curves. You consider the volume of a region, how that changes, and the equation satisfied by the volume is exactly the volume changes according to the integral of the divergence. So in a very real sense, a positive divergence means that things are spreading out just like the textbooks always say.